Voyager 1 has been flying for nearly 50 years. It is the most distant human-made object ever built, past the edge of the sun's protective bubble, out into genuine interstellar space, moving at about 17 kilometers every second. On Earth, that sounds fast. At that speed, it could circle the entire planet in less than 40 minutes. Now place Voyager at the start of a track exactly 1 light-year long and start a stopwatch. It would take approximately 17,600 years to finish that track, longer than all of recorded human history, long enough for entire civilizations to rise and disappear while Voyager keeps coasting. That is the first answer. But there is a second answer, and it is completely different. If you were the one traveling, not watching from Earth, the same journey could take less than 2 years. Both answers are mathematically correct. Both are experimentally supported. They describe the same distance. They are not describing the same clock. After 1 year, Voyager would have covered roughly 3.5 times the distance between Earth and the Sun. That is an immense journey by the standards of planetary exploration. But 1 light-year contains more than 63,000 Earth-Sun distances. The marker would still appear almost exactly where it began. The stopwatch would need to run for about 17,600 years before Voyager crossed the line. 17,600 years is longer than recorded human history. It is long enough for languages, borders, cities, and entire civilizations to appear and disappear while the spacecraft continues coasting. This is not because Voyager is defective or primitive. Its speed represents one of the greatest navigational achievements ever completed. Gravity assists from Jupiter and Saturn helped give it the outward motion it carries today. The problem is not the spacecraft. The problem is the scale on which the spacecraft is being judged. A light year is not a period of time. It is a distance. The distance light travels through a vacuum during 1 Julian year. Light covers that interval so quickly that using kilometers would bury the journey beneath a string of digits. 1 light-year is about 9.46 trillion kilometers. Even Voyager's 17 kilometers per second becomes almost motionless beside it. There is a faster human-made object. During its closest passages around the Sun, Parker's solar probe reaches about 192 kilometers per second. It is the speed record holder, moving more than 11 times faster than Voyager. If a spacecraft could sustain that speed in a straight interstellar crossing, 1 light-year would take roughly 1,560 years. That is a dramatic improvement, but it is still nearly 20 ordinary human lifetimes placed end to end. There is also an important catch. Parker does not maintain that speed while escaping toward another star. It reaches its record near the Sun because it is falling through an intense gravitational field on a tightly stretched orbit. As Parker climbs away again, it slows. Its peak speed is real, but treating it as a permanent interstellar cruising speed is a useful comparison, not an actual mission plan. So the first answer to the question is severe but clear. With a spacecraft moving like Voyager, 1 light-year requires about 17,600 years. With Parker's brief record speed somehow maintained, it would still require about 15 centuries. Neither figure includes the time needed to accelerate at departure or slow down at arrival. They are clean benchmarks. 1 fixed distance divided by 1 assumed constant speed. But those benchmarks leave several empty spaces on the mission board. What kind of vehicle is traveling? How does it gain its speed? Must it stop at the destination, or merely fly past? Most importantly, whose stopwatch supplies the answer? At Voyager's speed, the clock on the spacecraft and the clock on Earth remain almost perfectly synchronized. At far greater speeds, they do not. A traveler can cross the same interval and record less time than the people who remain behind. This is not a faulty clock, a visual trick, or a science fiction loophole. It is a measured feature of nature. Before any engine is chosen, then, the question already contains a hidden disagreement. Earth can measure one duration, while the ship measures another. A mission that arrives at high speed also has a different answer from one that stops. Speed alone is not enough. A complete crossing needs a trajectory, an arrival condition, and two carefully labeled clocks recording the same voyage in reality. The distance marker has not moved. The light year has not changed. Yet the answer can shift from thousands of years to several years, and under an ideal acceleration profile, the travelers could record less than 2. To understand how all of these answers can be correct, the stopwatch needs a second clock, and the journey needs rules that no existing spacecraft has ever been able to test at full scale. The first stopwatch gave us a useful answer, but not a complete one. 17,600 years describes a spacecraft moving at Voyager's speed. Change the speed, and the answer changes. Change the way the spacecraft accelerates, and it changes again. Ask what the travelers themselves record, rather than what Earth records, and eventually the two answers separate. The question therefore needs more than a distance. It needs a mission. Begin with light itself. A light year is defined as the distance light travels through a vacuum during 1 Julian year. In the frame where the departure point and destination remain 1 light year apart, a light signal crosses that distance in exactly 1 year. It does not mean a spacecraft can make the same journey in 1 year. Anything with mass can approach the speed of light, but it cannot reach it. Now return to the machines humanity has actually built. At roughly 17 kilometers per second, Voyager supplies our first benchmark, about 17,600 years. Parker's solar probe briefly reaches around 192 kilometers per second near the Sun. If that peak speed could somehow be maintained on a straight course, the same distance would take about 1,560 years. Parker does not perform such a journey, but the comparison reveals how little even a major speed record changes the interstellar problem. Suppose a future probe could travel at 1/10 the speed of light, written as 0.1 c. Once it reached that cruising speed, and ignoring the time required to accelerate or slow down, it would cover 1 light year in 10 years according to Earth. This is already hundreds of times faster than Voyager, yet the journey still occupies a substantial part of a human life. At 0.2 c, the Earth frame crossing falls to 5 years. This is the speed often associated with concepts for extremely small laser-driven probes. It is not an achieved spacecraft speed, and it does not describe a crewed vehicle. It is a proposed target for gram-scale machines pushed by an enormous beam of light. Even then, 5 years describes the cruise across 1 light year, not the complete voyage to a real star, and not the development, launch, acceleration, communication, or braking time. For the traveler moving at 0.2 c, the elapsed time would be slightly shorter, about 4.899 years. The difference is small because 1/5 of light speed, though extraordinary for engineering, is still modest in relativistic terms. The ship's clock has begun to separate from Earth's clock, but only slightly. At half the speed of light, Earth measures 2 years for the crossing. The ship measures about 1.732 years. At 0.9 c, Earth measures about 1.111 years, while the ship records only about 0.484 years. These examples assume that the spacecraft is already moving at its stated speed when the measured crossing begins, and continues without slowing when it passes the marker. No real vehicle can change speed instantaneously. The faster the example becomes, the more serious that missing part of the story becomes. There is another way to describe the journey. Instead of choosing a cruising speed, choose an acceleration that travelers could understand directly. Imagine a ship whose onboard accelerometer continuously reads one standard Earth gravity. The passengers would feel pressed toward the floor, much as they do while standing on Earth, even though the ship is far from any planet. If it accelerated for half the distance, turned its thrust direction, and decelerated for the other half, it would arrive at rest beside the destination marker. According to the ideal equations, Earth would measure about 2.208 years from departure to arrival. The travelers would measure about 1.892 years. During the journey, the ship would reach a maximum speed near 0.752 c. These values follow from established relativistic motion, but the vehicle itself does not exist. The calculation assumes continuous thrust, perfect operation, no shortage of energy or reaction mass, and no damage from the environment. It tells us what a trajectory would do, not how to build the machine that follows it. This produces a ladder of answers. Achieved spacecraft performance gives thousands of years. A proposed 0.2 c probe gives 5 Earth years for each light year of cruise. An ideal one-gravity mission that accelerates and then stops gives a little more than 2 Earth years, while its passengers experience a little less than 2. Light takes 1 Earth year, but no massive spacecraft can occupy that final row. None of these answers is false. Each answers a different version of the question. The error begins when a number is separated from the conditions that produced it. A complete answer must identify at least 4 things. First is the speed or acceleration profile. Does the craft coast at a fixed velocity or continue gaining speed? Second is the reference frame. Are we reading clocks on Earth or aboard the ship? Third is the arrival condition. Does the craft stop or flash past the destination at a large fraction of light speed? Fourth is the propulsion and payload class. Are we describing a tracked spacecraft, a gram-scale concept, or an ideal vehicle with no known engine? There is also a broader kind of time that does not belong in the crossing calculation but matters to any real program. A mission requires years of design, construction, testing, launch preparation, and perhaps assembly of infrastructure in space. A fast probe must return information, adding the light travel delay of its signal. These delays should not be secretly folded into the answer, but neither should they be forgotten when a theoretical transit is presented as a practical mission. The word "really" in the title demands this discipline. It does not ask only what the equations permit. It asks which clock is running, what path the vehicle follows, and what physical system makes that path possible. The shortest calculation may be the least achievable. The slowest calculation may be the one supported by an actual spacecraft still transmitting data. Before those answers can be judged, the mission board needs clear definitions: distance, speed, acceleration, proper time, coordinate time, and arrival must each occupy their own place. Only then can two clocks describe one journey without contradiction. And only then can we discover which part of the problem belongs to relativity and which part belongs to the machine. To compare the answers fairly, imagine a simple course laid out through empty space. At one end is a departure station. At the other is a destination marker. Both remain at rest relative to each other, and the distance between them is exactly 1 light-year. Each carries a clock. Before the journey begins, the clocks are synchronized. A third clock is placed aboard the spacecraft. This is the two-clock flight board, although it contains 3 physical clocks. The 2 station clocks belong to one shared reference frame, so together they define the time assigned by Earth and the destination. The onboard clock follows the spacecraft. Beside those readings, the board displays distance remaining, velocity, acceleration, and whether the vehicle must stop. Every travel time in the documentary must be tied to these fields. The first field is distance. The speed of light in vacuum is exactly 299,792,458 meters per second. A Julian year contains 365.25 days, with each day defined as 86,400 seconds. Multiply those values, and the result is 9,460,732,580,800 meters. That length is 1 light-year. It is about 9.46 trillion kilometers, or roughly 63,241 times the average distance between Earth and the Sun. The calculation explains why the unit contains the word year without turning it into a measure of time. A meter can be defined through how far light moves during a fraction of a second, yet a meter remains a length. In the same way, a light year is built from a speed and a duration, but the result is a distance. The title asks how much time a particular traveler needs to cross that distance. The second field is velocity. Velocity includes both speed and direction. For a simple straight crossing, direction remains fixed until the ship begins braking, so speed supplies most of what we need. If the craft coasts at a constant velocity of 0.2 c, the station frame divides 1 light-year by that speed and obtains 5 years. This calculation is valid within its stated conditions. Its weakness is not the arithmetic. Its weakness is that it begins after the spacecraft has somehow reached 0.2 c and ends before it has slowed down. That missing process belongs to the third field, acceleration. Acceleration is the rate at which velocity changes. A ship can accelerate by increasing its speed, decreasing it, or changing direction. An engine does not directly provide speed. It provides force over time, producing acceleration while consuming or receiving energy and exchanging momentum. The complete velocity profile is therefore a history, not a single number. There are 2 useful ways to describe acceleration. The stations can measure how the spacecraft's velocity changes according to their coordinates. The travelers can measure proper acceleration with an accelerometer aboard the ship. Proper acceleration is what produces the familiar sensation of being pressed into a seat or supported by a floor. A spacecraft coasting freely can move extremely fast relative to Earth, while its accelerometer reads 0. A stationary person standing on Earth feels support from the ground, and an accelerometer reads approximately 1 standard gravity. This distinction allows the ideal 1 gravity scenario to be stated precisely. The ship's onboard accelerometer is assumed to read about 980,665 meters per second squared during the powered phases. The phrase does not mean the ship is pulled by Earth's gravity. It describes the acceleration the travelers physically feel. It also does not identify an engine capable of maintaining that reading. It defines a trajectory so its timing can be calculated. The fourth field is the reference frame. A reference frame is a system for assigning positions and times to events. The departure and destination stations share one convenient frame because they remain a fixed light-year apart. Their synchronized clocks provide coordinate time for the crossing. Coordinate time answers questions such as, when did the ship leave the departure station? And when did it reach the destination, according to observers for whom both endpoints are stationary? The onboard clock measures proper time. Proper time is the duration recorded by a clock that travels along the spacecraft's path through space-time. It is not an estimate made from far away. It is the time physically accumulated by the ship's clock between departure and arrival. The travelers age according to this duration. At ordinary spacecraft speeds, proper time and station frame time differ by so little that the distinction can usually be ignored. Near light speed, it becomes central. Neither clock is secretly the correct one, while the other is mistaken. They measure different intervals along different paths. The station clocks remain separated in space and belong to the endpoint frame. The ship clock moves from one station to the other. Special relativity supplies consistent rules connecting their readings. The disagreement is not caused by communication delay. Observers can correct for the time taken by signals and still calculate the same difference. The fifth field is the arrival condition. A probe that passes the destination at 0.2 c has completed a crossing in the geometric sense, but it has not completed a rendezvous. At that speed it would cover enormous distances, while its instruments had only a short interval near the target. To arrive at rest, the spacecraft must remove the momentum it gained. That requires breaking through another force, another exchange of momentum, or infrastructure already waiting near the destination. This is why acceleration cannot be treated as a small detail added to the edges of a cruise. If a mission accelerates for half the distance and decelerates for the other half, there may be no long coasting phase at all. Its maximum speed appears only around the midpoint. Its total time depends on the entire curve of acceleration, velocity, and braking. The board also needs one boundary between physics and engineering. Kinematics describes the motion, how position, velocity, acceleration, and time relate. It can calculate an ideal trajectory without naming an engine. Dynamics and engineering ask what forces create that trajectory, where the energy comes from, how momentum is exchanged, and whether the vehicle survives. A kinematically valid journey is not automatically a buildable one. The completed flight board now has everything required for an honest question. It asks for the endpoint frame distance, the full acceleration and velocity profile, the time on the station clocks, the proper time aboard the ship, the payload class, and the required state at arrival. Remove any one of these labels, and a dramatic number can become misleading. Those labels will prevent later calculations from answering different questions accidentally. For most of human history, however, one field would have seemed unnecessary. Time was assumed to flow identically for everyone. A moving clock and a stationary clock could disagree because one was faulty, but not because motion itself changed the interval they recorded. That assumption worked so well that abandoning it required more than imagination. It required a conflict between the rules of motion and the measured behavior of light. Before anyone could ask how long a spacecraft would need to cross a light year, astronomers had to learn how far away the stars were. For centuries, the stars offered direction, brightness, and motion across the sky, but no dependable scale. Their distances were so large that the ordinary geometry of human travel seemed powerless to reach them. The key was parallax. Hold one finger in front of your face and look at it first with one eye, then the other. The finger appears to shift against the distant background because the viewpoint has moved. Earth provides a far larger baseline. Astronomers can observe a nearby star from opposite sides of Earth's orbit and search for its tiny apparent shift against more distant stars. If the angle is measured, geometry gives the distance. In 1838, Friedrich Bessel reported a successful stellar parallax measurement for 61 Cygni. The angle was extremely small, but it placed the star at an almost unimaginable distance. Light itself required years to cross the gap. The stars were no longer points fixed to a nearby celestial shell. They occupied a depth of space so great that light travel time became one of the most natural ways to describe it. This did not immediately create the modern definition of the light year, but it established the conceptual need. Kilometers were technically valid and practically awkward. A unit based on light-connected distance to the fastest known signal in nature. It also turned every stellar measurement into an implied journey. To state that a star was 10 light-years away was to say that even its light had been traveling for 10 years before reaching the observer. The physics used to imagine a material journey remained classical. In Newtonian mechanics, space provides a shared stage, and time flows uniformly for everyone. If two synchronized clocks are separated and one begins moving, both still belong to the same universal time. Their readings should agree unless a clock is damaged or affected by some ordinary physical disturbance. Velocities also add in the familiar way. A passenger walks forward inside a moving train. Someone beside the track measures the train's speed plus the passenger's walking speed. Throw an object from the train, and the same rule applies. This principle succeeds throughout daily life, navigation, artillery, and much of astronomy. At speeds far below that of light, it remains an excellent approximation today. Under these rules, the travel time problem seems complete. Measure a distance. Choose a speed. Divide the first by the second. If a craft travels at 1/10 of light speed, it needs 10 years to cross 1 light year, and every reliable clock should agree. Faster engines reduce the time in direct proportion. Nothing in the classical calculation creates a second answer for the travelers. Rocketry added a different limitation. A vehicle cannot increase its speed merely by deciding to move faster. It must exchange momentum. In 1903, Konstantin Tsiolkovsky published the relation now called the rocket equation. A rocket accelerates by throwing exhaust backward. Because it carries its propellant with it, the vehicle must first accelerate fuel that will be used later to accelerate the remaining vehicle. The result is an exponential relationship between the desired change in velocity and the ratio of initial mass to final mass. Reaching twice the velocity change does not simply require twice the propellant. The exact ratio depends on exhaust velocity, but the compounding structure is unavoidable for an ideal reaction rocket carrying its own fuel. Long before a spacecraft approaches relativistic speed, propulsion can become dominated by propellant. This equation did not make rockets impossible. It made their design quantitative. Chemical rockets work because their missions demand velocity changes compatible with their exhaust speeds, and because stages discard empty tanks and engines. Planetary gravity assists can also exchange momentum with moving worlds, reshaping a spacecraft's solar orbit without requiring it to carry all the necessary propellant. Voyager's journey emerged from this classical world of momentum, energy, orbital motion, and shared time. Yet another part of 19th-century physics was creating a conflict. James Clerk Maxwell's electromagnetic theory described light as a wave traveling at a characteristic speed, determined by the properties of electric and magnetic fields. The equations did not behave like a simple ball thrown from a train. If ordinary velocity addition applied, observers moving toward or away from a light beam should measure different light speeds. Physicists tried to understand what medium or preferred state of motion might define the wave's true speed. Experiments, including the famous work of Albert Michelson and Edward Morley, failed to reveal the expected motion through such a medium. That result did not single-handedly produce special relativity, and the history involved several investigators and mathematical developments. But the wider problem became increasingly difficult to ignore. Electromagnetism and classical transformations did not fit together cleanly. The conflict was not that Newtonian mechanics had suddenly stopped predicting falling objects, planets, or trains. Its success remained. The problem appeared when the same rules were pushed toward light. A model can be extraordinarily accurate inside one range and still become an approximation inside a deeper framework. The task was to preserve what worked while changing the assumptions that failed. In 1905, Albert Einstein began from two principles. The laws of physics should take the same form in every inertial frame, and light in vacuum should have the same measured speed for every inertial observer, regardless of the motion of the source or observer. Taken together, these principles did not allow time to remain universal. Imagine two observers moving relative to each other, each measuring the same flash of light. Classical velocity addition says they cannot both obtain the same speed unless one observer's measurements of distance, time, or simultaneity differ from the other's. Einstein's framework accepted that consequence. The speed of light did not adjust itself to preserve an absolute clock. Measurements of space and time adjusted in a precise, connected way. This was not permission for anything to move faster than light. It was a replacement for the rule that had made such a limit difficult to understand. The new framework would preserve causality and make the old equations reappear at low speed, while predicting unfamiliar behavior near light speed. Moving clocks would accumulate different intervals. Distances measured along the direction of motion would differ between frames. Events judged simultaneous by one observer would not always be simultaneous for another. The two-clock flightboard now had a historical reason to exist. Bessel's parallax had made the distance measurable. Classical mechanics had supplied the first travel time. Tsiolkovsky had shown that changing velocity carried a mass cost. Electromagnetism had challenged ordinary velocity addition. Einstein then changed the relationship between the two clocks. The ruler was ready. The journey remained entirely imaginary. But a new theory does not make old spacecraft faster. It changes what their speed means, and what will happen if engineering ever pushes them into the relativistic regime. Before following those transformed clocks, the scale of the technological gap must be faced directly. Humanity has produced machines that fall around the sun at record speeds, and probes that coast into interstellar space. Against a light year, even these triumphs barely start the stopwatch. Humanity has never built a machine that can cruise through interstellar space at anything close to a significant fraction of light speed. Yet the spacecraft speed record can make the gap appear smaller than it is. Parker Solar Probe moves at roughly 192 kilometers per second during its closest approaches to the Sun. Voyager 1 moves outward at only about 17. If Parker is more than 11 times faster, why is Voyager the more useful starting point for an interstellar journey? The answer lies in the difference between peak speed and sustained escape speed. Voyager 1 was launched in 1977 for a mission among the outer planets. Its rocket provided the initial energy, but the mission also used the motion and gravity of Jupiter and Saturn. As Voyager approached a planet, the planet pulled it inward and changed its direction. In the Sun's reference frame, the encounter allowed the spacecraft to exchange a tiny amount of momentum with the moving planet. The planet's change was immeasurably small, while the lightweight probe received a valuable alteration to its solar trajectory. After Saturn, Voyager 1 was directed above the main plane of the solar system and continued outward. It eventually crossed the heliopause, the boundary where the solar wind yields to the surrounding interstellar medium. Crossing that boundary did not place Voyager beyond every possible reach of the Sun's gravity, but it did make the craft the first human-made object confirmed to enter interstellar space in the environmental sense. Voyager now travels at about 17 kilometers per second relative to the Sun, or roughly 3.5 astronomical units each year. This is not a brief burst recorded near a planet. It is an outward coasting speed on an escape trajectory. Voyager was not designed to reach another star, and it is not aimed at a destination exactly 1 light-year away. But its persistent motion gives us a real benchmark for a spacecraft leaving the planetary system. At that speed, 1 light-year takes about 17,600 years. In terms of light speed, Voyager moves at approximately 0.0007 c. Written as a percentage, that is about 0.0057% of light speed. The number is so small that the relativistic difference between Earth's clock and Voyager's clock is negligible for the purpose of this comparison. Parker Solar Probe reaches a very different kind of record. Its mission is to approach the Sun closely enough to study the solar corona and the processes that accelerate the solar wind. Reaching the Sun is not simply a matter of launching inward. Earth already travels sideways around the Sun at great speed. A spacecraft launched from Earth inherits that orbital motion, so it must lose substantial sideways velocity to fall much closer. Parker used repeated flybys of Venus to reshape its orbit and lower its closest approach. Near perihelion, the point where it passes closest to the Sun, solar gravity converts gravitational potential energy into kinetic energy. The spacecraft falls rapidly through the Sun's gravitational field and reaches about 430,000 miles per hour, or approximately 192 kilometers per second. It set that record in December 2024 and has matched it during later close passes. The achievement is extraordinary. Parker survives an environment of intense heat and radiation while moving faster than any previous human-made object. But it is not firing an engine that could hold 192 kilometers per second on a straight path to the stars. It remains in an elongated orbit. As it climbs away from the Sun, kinetic energy returns to gravitational potential energy, and the craft slows. At the next close approach, it accelerates again. If the record speed were treated as a constant interstellar cruising speed, simple division gives approximately 1,560 years per light year. That figure is useful because it shows that even humanity's highest measured spacecraft speed remains far below a human-scale interstellar velocity. It is not a forecast for Parker, and it is not proof that an existing propulsion system could maintain the same motion after escaping the Sun. The distinction matters because speed has no single universal value without a reference frame. Parker's record is normally reported relative to the Sun, near perihelion. Voyager's outward speed is also described relative to the Sun. Using the same reference makes the comparison meaningful, but their trajectories remain fundamentally different. One is a repeated gravitational plunge on a bound orbit. The other is a sustained outward coast. Now place both craft on the speed ladder. Voyager occupies about 0.00064 c. Parker's peak reaches about 0.00064 c, or roughly 0.064% of light speed. A probe at 0.1 c would move around 156 times faster than Parker at its peak, and roughly 1,760 times faster than Voyager. A 0.2 c probe would double that requirement again. This is not a gap that disappears through one stronger launch vehicle or one additional gravity assist. Rockets can improve departure speed. Planetary encounters can exchange momentum. A close solar passage can create an enormous peak velocity. But an interstellar craft must leave with positive escape energy in the desired direction and retain a useful cruise velocity after it has climbed away from the Sun. Falling deeply into a gravitational field produces speed near the bottom. It does not create unlimited energy at infinity. The real measure of difficulty is therefore not a dramatic speedometer reading alone. It is the energy and momentum associated with the complete trajectory. A record set during a fall, a speed sustained during escape, and a cruise velocity maintained between stars answer different engineering questions. The flight board must keep those labels visible. The comparison also reveals why ordinary intuition fails. Increasing a car's speed from 50 to 100 kilometers per hour feels like a large change because it halves the travel time. Increasing Voyager's speed 11-fold to Parker's peak does the same mathematically, reducing 17,600 years to around 16 centuries. The improvement is immense, yet the remaining wait is still longer than the history of many civilizations. To reach 1 light-year in 10 Earth years, the craft must average 0.1 c across the measured interval. To do it in 5, it must average 0.2 c. Average speed is crucial. A vehicle that briefly touches a high peak but spends most of its journey accelerating slowly will take longer. A vehicle that must brake before arrival will also have a lower average than its maximum. This explains why statements about the fastest spacecraft can mislead without being factually wrong. Parker owns the peak speed record. Voyager provides a clearer example of long-term outward motion. Neither is remotely close to the speed assumed in relativistic interstellar proposals. The important anomaly is not a disagreement between observation and theory. It is the enormous distance between a trajectory that physics allows and a trajectory engineering has demonstrated. On the board are 3 columns. Peak velocity describes the fastest moment. Cruise velocity describes the motion that can persist between stars. Mission average velocity includes every slower period of acceleration and braking. Only the last determines total travel time. A spectacular peak can transform a record without transforming the journey, while a lower sustainable speed may matter far more. That gap creates the next question. Perhaps current spacecraft are slow only because their engines are limited. Perhaps a future machine could continue accelerating until 1 light-year became a journey of years, rather than millennia. But once velocity becomes a substantial fraction of light speed, the old rule of simply adding more speed no longer works. The clocks begin to separate, distances depend on the frame, and every further increase in velocity demands a rapidly growing amount of energy. The fastest machines still crawl because the interstellar ruler is vast. To understand what happens when crawling finally becomes relativistic flight, the universal clock must now be taken apart. The old travel calculation assumes that every accurate clock shares the same time. Special relativity begins by removing that assumption. It does not do so arbitrarily. It does so because two principles must remain true together. The laws of physics have the same form for every inertial observer, and every inertial observer measures the same speed for light in a vacuum. An inertial observer is one who is not accelerating. Imagine a spacecraft coasting smoothly, while a station remains at rest relative to the departure and destination. Inside the sealed ship, ordinary experiments work normally. A ball tossed across the cabin follows the expected path. No local test of motion reveals a special state called absolute rest. The station can say the ship is moving, while the ship can say the station is moving. Their relative motion is what matters. Now place a simple clock inside the spacecraft. Two mirrors face each other, one above the other. A pulse of light travels from the lower mirror to the upper mirror and back. Each round trip is one tick. For someone aboard the ship, the pulse moves vertically through the cabin. If the distance between the mirrors is known and light speed is fixed, the duration of each tick is fixed. The station sees something different. While the pulse travels upward, the spacecraft moves sideways. The light therefore follows a diagonal path from the lower mirror's earlier position to the upper mirror's later position. The diagonal is longer than the vertical path measured aboard the ship. Yet the station cannot say that light simply traveled faster to cover the extra distance. Light speed must still be the same. The station must conclude that more time passed between the ticks of the moving clock. This is time dilation. The moving clock accumulates less time between the same pair of events than the station's coordinate clocks assign to them. The result is not caused by imperfect machinery. Replace the light clock with an atomic clock, a chemical reaction, a heartbeat, or the decay of an unstable particle, and every physical process follows the same relativistic timing. The amount of dilation is described by the Lorentz factor, written with the Greek letter gamma. Gamma equals 1 divided by the square root of 1 minus the velocity squared, as a fraction of light speed. The structure matters more than memorizing the formula. At low velocity, the fraction is tiny, and gamma remains almost 1. Near light speed, the denominator approaches 0, and gamma grows rapidly. At Voyager's speed, gamma is so close to 1 that the clock difference is irrelevant to our rounded 17,600-year estimate. At 0.2 c, gamma is about 1.0206. Earth assigns 5 years to a constant speed crossing, while the ship records about 4.899. Relativity has begun to matter, but it has not transformed the journey. At 0.5 c, gamma rises to about 1.1547. Earth assigns 2 years and the ship records about 1.732. At 0.9 C, gamma is about 2.294. Earth assigns roughly 1.111 years to 1 light-year, while the ship records about 0.484. The ship does not measure itself moving through a strangely slowed internal time. Its clock, thoughts, and biological processes remain normal locally. The difference appears when the elapsed time between departure and arrival is compared with the clocks belonging to the endpoint frame. This raises an apparent symmetry. If the station says the moving ship's clock runs slowly, the coasting ship can say the station's clocks are moving and therefore run slowly. Neither inertial frame is privileged. The resolution begins with simultaneity. Comparing distant clocks requires deciding which separated events occur at the same time, and observers in relative motion do not make that assignment identically. The station frame synchronizes the departure and destination clocks using light signals and its own definition of simultaneous events. The moving ship has a different set of simultaneous slices through those locations. Consequently, its account of the distance between endpoints and the readings on separated station clocks differs from Earth's account. This is not a communication mistake. It remains after signal delays are calculated correctly. For a journey that begins and ends in the endpoint frame, the symmetry does not prevent the clocks from being compared. The spacecraft must change its motion to depart from rest, and if it arrives at rest, it must change motion again. The complete ship path is not one unbroken inertial frame. Acceleration makes the travel histories different, although it is misleading to say acceleration alone directly causes all time dilation. The elapsed proper time depends on the entire path through space-time. Time dilation has a spatial partner, length contraction. In the station frame, the departure and destination remain 1 light-year apart. A spacecraft moving relative to them assigns a shorter distance between those endpoints along the direction of motion. At 0.9 C, that contracted distance is roughly 1 light-year divided by gamma. The ship's shorter travel time and shorter measured distance fit together so that it still measures light moving at exactly C. Nothing at the endpoints is physically squeezed in its own rest frame. The station observers continue to measure 1 light-year. Length contraction describes the distance between simultaneous endpoint positions in the moving frame, and simultaneity differs between frames. The result cannot be understood by imagining one universal snapshot viewed from different angles. Each frame constructs its own consistent measurement of distant events. This is the hidden mechanism behind the two clocks. Earth's coordinate time, the ship's proper time, and the ship frame distance are connected by the same transformation. One does not change independently to create a convenient answer. If the travelers record less time, their frame also assigns the journey a correspondingly shorter distance. Both still measure the same local speed of light. A useful way to join these effects is to stop thinking of the spacecraft as moving only through space. It traces a path through space-time. Proper time is the interval accumulated along that path. Two clocks that separate, follow different world lines, and reunite can display different totals even when both function perfectly. The difference belongs to the routes they took. This does not mean a traveler can choose any elapsed time without consequence. Reducing proper time requires a world line that stays close to the path light would follow, which means reaching an enormous relative speed. The ship must first gain the required momentum and, for a rendezvous, later lose it. Relativity can shorten the time recorded on board, but it never provides the acceleration for free. The idea also prevents a common mistake. Time dilation is not merely what Earth sees while delayed images arrive from the ship. Light signals can make an approaching clock look fast, or a receding clock look slow because of changing signal distance. That Doppler effect can be removed mathematically. Special relativity also changes the cost of increasing velocity. In classical mechanics, kinetic energy grows with the square of speed. That approximation works at low velocities. Relativistically, kinetic energy depends on gamma. The energy above rest is gamma minus 1, multiplied by the mass and by the speed of light squared. As gamma rises, the energy required for each further increase becomes increasingly severe. Older explanations sometimes say an object's mass becomes infinite at light speed. That language can confuse the issue. The object's invariant or rest mass does not increase. Its energy and momentum grow without bound as its speed approaches c. A finite engine supplying finite energy can push a massive craft closer and closer to light speed, but it can never complete the final step to c. This is not like an aircraft failing to exceed a design limit because its engine is weak. It is built into the geometry and energy-momentum structure of special relativity. Light follows a different kind of path because photons have zero rest mass. A spacecraft, passenger, dust shield, fuel tank, or scientific instrument has rest mass and cannot be accelerated onto that path. The speed limit therefore protects causality, while permitting enormous differences in elapsed time. In the endpoint frame, a massive craft crossing 1 light-year must take more than 1 year. On board, however, the proper time can be much shorter if the craft travels close enough to see. There is no contradiction because the traveler is not measuring the same spatial interval or using the same distant simultaneity as the endpoint frame. Return to the flight board. The departure and destination clocks agree that they are 1 light-year apart. The ship clock follows another route between their departure and arrival events. At low speed, all readings nearly match. At high speed, the ship accumulates less proper time. The destination has not moved in the endpoint frame, and the spacecraft has not exceeded light. The geometry connecting space and time has replaced the universal stopwatch. These conclusions are mathematically consistent, but a documentary about real travel cannot stop at consistency. The 2-clock prediction must survive contact with nature. If moving clocks truly accumulate less time, unstable particles should live longer when moving rapidly. Transported atomic clocks should return with changed readings, and accelerators should require ever more energy to push massive particles closer to light speed. Relativity made those predictions before any interstellar ship existed. Experiments would decide whether the transformed clock belonged to the universe or only to the equations. Special relativity asks us to accept that 2 reliable clocks can separate, reunite, and display different elapsed times. An interstellar spacecraft would provide a dramatic demonstration, but the theory did not have to wait for one. Nature already produces moving clocks in the form of unstable particles, and laboratories can accelerate those particles far beyond any spacecraft speed. Muons provide one of the clearest examples. A muon is an unstable elementary particle. When created at rest, it survives on average for only a tiny fraction of a second before decaying. Cosmic rays striking atoms high in Earth's atmosphere produce muons many kilometers above the ground. Even moving close to light speed, A classical calculation using their rest frame lifetime predicts that relatively few should survive long enough to reach the surface. Yet muons are detected at ground level in large numbers. From Earth's frame, their internal decay clocks run slowly because the particles are moving rapidly. Their lifetimes are dilated, allowing more of them to cross the atmosphere before decaying. From the muons' associated moving frame, the explanation is expressed through contracted distance. The atmosphere is thinner along the direction of motion. The two descriptions are different views of the same relativistic interval. Controlled accelerator experiments remove much of the uncertainty found in a natural cosmic ray source. Researchers create unstable particles, accelerate them to known velocities, and measure how long they survive. The observed lifetimes increase by the Lorentz factor predicted from their speed. The particles do not merely look delayed because their signals take longer to arrive. Their decay statistics change according to the proper time accumulated along their paths. The muon example also demonstrates why a decay process can serve as a clock without containing hands or gears. A large population has a statistically predictable lifetime. Motion does not select a few unusually durable particles and leave the rest unchanged. It changes the relationship between the laboratory's elapsed time and the proper time governing the population. When velocity changes, the measured lifetime changes by the predicted factor. Precision clock tests make the comparison more literal. Two clocks can be synchronized, sent along different routes, and brought together again. Once known influences are included, their final disagreement matches the difference expected from their motion and gravitational history. The effect may be tiny at aircraft or satellite speeds, but precision instruments can resolve it. The principle is identical to the flight board. Clocks following different paths need not accumulate identical time. Accelerators then extend the test into the regime spacecraft designers would care about. Magnetic fields bend charged particles, and the curvature of their paths reveals momentum. As more energy is supplied, the measured momentum continues rising, even while velocity crowds ever closer to light speed. Energy has not vanished, and the machine is not failing. The relativistic relationship predicts where that energy goes. This is why the speed limit is inferred from measurable dynamics, rather than from the absence of a sufficiently powerful rocket. Agreement persists across controlled measurements. Atomic clocks test the same structure with objects we can carry. Extremely precise clocks have been transported on aircraft and compared with clocks that remained behind. Their readings differ by amounts consistent with relativity, once both motion and gravitational conditions are included. Modern satellite navigation also requires relativistic timing corrections. Satellite clocks move relative to receivers on Earth and occupy a different gravitational environment. Special relativity and general relativity contribute separate corrections, and both must be handled for accurate positioning. This does not mean satellite navigation is a pure test of the 1 light-year journey. The speeds are far smaller, and Earth's gravity matters. Its importance is practical. Relativistic clock differences are not decorative ideas reserved for distant stars. They are part of operational systems that depend on precise timing. Particle accelerators test another prediction that matters directly to travel. Apply more energy to an electron or proton, and its speed rises. At first, classical intuition works reasonably well. As the particle approaches light speed, however, additional energy produces smaller increases in velocity, while momentum continues to grow. Massive particles can be driven extremely close to C, but never reach or cross it. If the classical relation between energy and speed remained valid, a sufficiently powerful accelerator could push a particle through the light barrier. Instead, measurements follow the relativistic energy-momentum relation. This supports the same rule that governs a spacecraft. There is no finite final push that takes an object with rest mass to light speed. These experiments establish a crucial boundary in the documentary. Relativistic kinematics is not the speculative part of interstellar travel. Time dilation, proper time, the behavior of fast particles, and the energy growth near C are supported by extensive evidence. What remains speculative is the engineering system that could apply those rules to a large, protected spacecraft over interstellar distances. With that boundary clear, the flight board can be filled for several constant speed crossings. These are not complete missions. Each begins with the spacecraft already moving at its stated speed as it passes the departure marker, and each ends when it passes the destination without braking. Their purpose is to isolate the relationship between velocity and the two clocks. At 0.2 c, the Earth frame calculation is simple. 1 light-year divided by 1/5 of a light-year per year equals 5 years. Gamma is approximately 1.0206, so the onboard proper time is about 5 years divided by that factor, or 4.899 years. Engineering has changed enormously from Voyager, but the relativistic clock difference remains modest. At 0.5 c, Earth records 2 years. Gamma is approximately 1.1547, giving about 1.732 years aboard the ship. The difference is now measured in months. The travelers would still experience every onboard process normally. They would simply arrive having accumulated less time than the synchronized endpoint clocks. At 0.9 c, Earth records about 1.111 years for the 1 light-year interval. Gamma is approximately 2.294, so the ship records about 0.484 years. The endpoint frame duration is approaching the 1-year light travel limit, while the proper time has fallen below half a year. The same journey now has 2 visibly different, but experimentally grounded answers. The pattern becomes more extreme closer to light speed. At 0.99 c, Earth still records just over 1 year, approximately 1.010 years, because the craft remains below C. Gamma is about 7.09, and the onboard time is roughly 0.142 years. The travelers could record only weeks while the endpoint clocks record more than a year. But the energy and acceleration omitted from the example have become vastly more demanding. These rows must not be read as a menu of available spacecraft. A constant speed transit hides the entire process that creates the speed. A real ship begins at rest relative to its departure system. Reaching 0.9 c or 0.99 c requires time, distance, energy, and an exchange of momentum. If the ship must arrive at rest, the same problem returns in reverse. The experiment-supported conclusion is narrower and stronger. If a massive craft could coast at those velocities, the station and ship clocks would accumulate the listed intervals. The calculations are conditional, but the physics connecting velocity to elapsed time is not an unsupported guess. This distinction protects both skepticism and wonder. We do not need to pretend that a near-light-speed vehicle exists in order to trust the clock calculation. We also do not need to treat a correct equation as proof that the vehicle can be built. Evidence establishes what nature will do with a fast clock. engineering must establish whether a spacecraft can become that clock. There is one further limitation in every constant speed row. Instant acceleration would require an unphysical change in velocity. The ship cannot simply enter the departure marker at 0.9 c unless some earlier region of space and time has already been used to accelerate it. If the measured course begins with the vehicle at rest, its speed must grow throughout part of the 1 light-year distance. That change leads to a more realistic idealization. Instead of granting the ship a cruise velocity at the start, assign a proper acceleration that its passengers continuously feel. Let the vehicle build speed from rest. If it only needs to cross the marker, it can accelerate throughout the distance. If it must arrive at rest, it can accelerate for half the journey and brake for the other half. Relativity has passed the relevant tests. The clocks can now be trusted. What remains is to trace their readings through an accelerated journey. That calculation will overturn the remaining intuition that 1 light-year imposes almost the same experience duration on every traveler. The distance stays fixed in the endpoint frame. The speed limit remains intact, and yet the ship's path through space-time can make its own elapsed time unexpectedly short. The constant speed examples begin after the hardest event has already occurred. The ship enters the course moving at 0.2 c, 0.9 c, or 0.99 c, as though the velocity appeared without time, distance, or force. A better idealization begins with the spacecraft at rest beside the departure station and gives it an acceleration the travelers can measure. Set the onboard accelerometer to 1 standard gravity. Inside the ship, passengers feel a steady force pressing them toward the floor. Loose objects fall toward the rear of the cabin. The sensation resembles standing on Earth, although it is produced by thrust rather than by support against a planet's surface. The acceleration is approximately 9.80665 meters per second squared, as measured aboard the ship. This choice is useful because it is physically intuitive, not because an engine capable of maintaining it exists. The calculation assumes uninterrupted thrust, perfect control, and an unlimited means of supplying energy and momentum. It temporarily ignores fuel, heat, shielding, reliability, and the material struck along the route. Those costs will return. For now, the question is purely kinematic. What path would 1 gravity create? At first, the motion looks almost classical. Each second adds velocity. Earth and ship clocks remain close, and the distance covered during early acceleration is familiar. But the classical rule cannot continue indefinitely. If the ship simply gained 9.80665 meters per second every Earth frame second forever, it would eventually exceed light speed. Relativity prevents that result. The travelers can continue feeling the same proper acceleration, while observers at the stations see the velocity increase by smaller and smaller amounts. The craft approaches C without reaching it. Its motion follows a relativistic curve called hyperbolic motion. Proper acceleration remains constant aboard the ship, while coordinate acceleration measured in the endpoint frame declines as the velocity becomes relativistic. First, consider a ship that does not need to stop. It accelerates at 1 gravity across the entire light year and passes the destination at high speed. The endpoint clocks record approximately 1.714 years between departure and crossing. The onboard clock records about 1.294 years. At the destination marker, the ship is moving at roughly 0.871 c. This is already a striking result. Earth records more than the 1 year required by light, as relativity demands for a massive craft. The travelers record substantially less time than Earth, but their clock never behaves abnormally inside the cabin. During the faster portion, the endpoint separation measured in the ship's changing instantaneous frame is contracted. The ship's path accumulates less proper time than the station frame assigns to the journey. But this is not an arrival in the practical sense. At 0.871 c, the destination would flash past. The spacecraft would carry enormous momentum into whatever region it intended to study. A complete rendezvous requires the craft to end at rest relative to the destination. The trajectory must therefore be divided into 2 equal distance phases. For the first half-light year, the ship accelerates at 1 gravity. At the midpoint, it turns so the thrust points opposite its direction of motion. The passengers continue feeling the same pressure toward the floor, but the force now removes velocity. The craft decelerates through the second half and reaches the destination at rest. The clocks produce the documentary's central reversal. Earth and the destination record approximately 2.208 years. The travelers record about 1.892 years. The maximum speed, reached near the midpoint, is approximately 0.752 c. The ship never approaches the 0.99 c used in the most extreme constant cruise example. Yet its continuous acceleration keeps the total crossing within a few years. The second half is not merely the first half played backward from every viewpoint. The direction of proper acceleration changes, and the ship moves through a sequence of instantaneous inertial frames. Yet the symmetric endpoint frame setup gives equal acceleration and braking distances, allowing the vessel to finish with 0 relative velocity. The full result follows from integrating the proper time along that accelerated world line. The comparison between the 2 1-gravity profiles also shows why the arrival condition matters. Accelerating throughout produces the shorter reading, but leaves the ship moving too quickly to remain near its target. Spending half the route braking adds time and lowers the maximum speed, yet turns a crossing into a rendezvous. Neither answer is more relativistically correct. They describe different world lines with different endpoints. A number quoted without that velocity conceals the essential operational difference between passing a destination and reaching it. Before this calculation, the light year seemed to impose an almost universal duration. Light takes 1 endpoint frame year, so a massive traveler appeared condemned to experience at least something close to 1 year, plus the delays of acceleration. The 1-gravity journey reveals the mistaken assumption. The 1-year lower limit belongs to the endpoint frame for a causal crossing. It is not a universal minimum for the traveler's proper time. The light year itself has not shrunk in the frame where the stations remain at rest. Their rulers and synchronized clocks still assign the endpoints the same separation. The travelers, however, do not share one fixed inertial frame throughout the accelerated trip. During each high-speed portion, an instantaneous co-moving frame assigns a shorter distance along the direction of motion. The reduced onboard time and the frame-dependent distance are 2 sides of the same relativistic structure. Nor has the ship found a loophole through the speed limit. At every moment, local measurements keep light moving at sea, and the ship remains below it. The path becomes short in proper time because the spacecraft follows a different route through space-time, not because it outruns a light signal. The midpoint therefore changes the governing question. The problem is no longer whether relativity permits a human-scale elapsed time. It does. The ideal calculation gives less than 2 years aboard and a little more than 2 years at the endpoints for a stopped arrival. The problem is, what kind of physical system could create that world line? To execute the trajectory, a machine must accelerate every kilogram of payload, structure, shielding, life support, engine, and remaining propellant to about 0.752 c. It must sustain thrust for almost the entire journey. At the midpoint, it must reverse the direction of that thrust, then remove the accumulated momentum without failure. The numerical result contains no design for doing any of this. The distinction is essential. A physically allowed path is stronger than fantasy. It obeys established relativity and can be calculated precisely. But it is weaker than a mission proposal. It does not show where the energy comes from, how momentum is exchanged, or how the craft survives. Kinematics has opened the door, while engineering still stands far outside it. The 2-clock flight board now displays its most surprising row. Distance, 1 light-year. Departure and arrival, at rest. Proper acceleration, 1 gravity, reversed halfway. Maximum speed, 0.752 c. Earth time, 2.208 years. Ship time, 1.892 years. Every field is mathematically consistent, except the one labeled propulsion system, which remains empty. Filling that final field requires more than naming a futuristic engine. The journey carries a momentum bill, an energy bill, a heat bill, and a braking bill. The shorter time did not erase the distance. It transformed the distance into demands that grow more severe as the clocks separate. The 1 gravity calculation gives the ship a trajectory, but not a power source. It tells us how the clocks behave if the vehicle reaches 0.752 c and later returns to rest. It does not explain how a machine gains that velocity, what it must carry, or where the energy goes when it brakes. Those questions are not secondary details. Together they decide whether the calculated time belongs to a mission or only to a permitted world line. Begin with the payload alone. Relativistic kinetic energy is gamma-1 multiplied by mass and the speed of light squared. For a 1,000 kilogram object moving at 0.2 c, the kinetic energy is roughly 1.85 quintillion joules. At about 0.752 c, the peak speed of the stopped 1 gravity journey, the same bare mass carries roughly 46 quintillion joules. These figures are minimum kinetic energies, not mission budgets. They assume that the energy reaches the payload perfectly. They exclude the engine, fuel, tanks, radiators, shielding, instruments, and any structure needed to keep the object intact. They exclude losses while producing or transmitting the energy. They also describe acceleration only. If the payload must stop, its kinetic energy must be removed or redirected at the destination. The minimum energy figures also reveal why efficiency must be labeled carefully. A propulsion system can be highly efficient at converting one form of energy into exhaust or beam power, and still require an enormous source. The lower bound survives every improvement in machinery. Momentum introduces another constraint that energy comparisons sometimes hide. A power source can release energy without automatically producing thrust in the required direction. The vehicle needs an exhaust stream, an external beam, or another interaction capable of carrying opposite momentum. Even matter-antimatter annihilation, if available, would need its products controlled and directed. Energy density is not a complete engine. At arrival, the accounting must close. If braking exhaust is expelled forward, the ship slows while the exhaust carries momentum onward. If a sail reflects light, the radiation changes momentum. Every scheme leaves a signature outside the vehicle. Stopping is not the disappearance of motion. It is the transfer of momentum and energy into something else. The scaling creates the first trap. A crewed ship cannot be treated like an empty 1,000-kilogram block. Add habitat, life support, redundancy, radiation protection, propulsion equipment, and supplies, and every kilogram joins the energy bill. If shielding is increased to survive high-speed impacts, the shield itself must be accelerated. If the engine becomes larger to provide more power, the larger engine must also be accelerated. Energy alone does not tell the entire story. A ship must also exchange momentum. A car pushes against the road. An aircraft pushes air backward. A rocket in vacuum carries material that it ejects as exhaust. The spacecraft gains forward momentum, while the exhaust gains momentum in the opposite direction. Conservation is satisfied, but the ship must transport the means of performing that exchange. The rocket equation describes the result. For a reaction rocket carrying its own propellant, the required ratio between starting mass and final mass grows exponentially with the demanded change in velocity relative to the exhaust velocity. A higher exhaust velocity improves the ratio because each unit of propellant carries away more momentum. But no choice removes the dependence on the full velocity change. This is why a dramatic claim about a fuel tank larger than a planet is meaningless without specifying an engine. A chemical rocket, a nuclear system, a fusion exhaust, and an ideal photon rocket have very different effective exhaust velocities. Their mass ratios cannot be discussed with one universal number. The responsible conclusion is structural. When the required velocity change greatly exceeds the exhaust velocity, onboard propellant compounds severely. The stopped one-gravity journey demands more than a peak speed of 242 c. The ship must build that velocity and then remove it. In rocket terms, the total mission change in velocity includes both phases. Propellant reserved for braking must be carried during acceleration, and propellant needed earlier must accelerate the later braking propellant. Staging can discard empty components, but it cannot cancel conservation of momentum. There is also a power problem. Energy is an amount. Power is the rate at which that energy is delivered. Maintaining one gravity for a massive vehicle over most of the journey requires an extraordinary continuous energy flow. The propulsion system must convert stored or received energy into directed momentum while limiting waste heat. Any inefficiency becomes heat that must be kept away from passengers, electronics, tanks, and structural materials. Space is cold, but cooling in vacuum is not automatic. A spacecraft cannot release heat through surrounding air. It must radiate energy away, as electromagnetic radiation. And radiator performance depends on area and temperature. Larger radiators add mass. Higher operating temperatures challenge materials. The system that prevents the ship from overheating therefore becomes another object that the propulsion system must accelerate. One proposed escape from the onboard fuel trap is to place the energy source elsewhere. A powerful beam can strike a sail and transfer momentum through reflected or absorbed light. The spacecraft no longer carries the entire power plant or conventional reaction mass. This can transform the mass ratio, especially for an extremely light probe. But the momentum bill has not disappeared. The beaming system must generate and direct the energy. The sail must survive the beam without absorbing enough heat to fail. The beam must remain focused and accurately pointed, while the craft accelerates across a vast distance. Most importantly, a beam located near the departure point naturally accelerates the vehicle away. It does not automatically brake the craft near the destination. A second beam waiting at the destination could in principle help, but placing that infrastructure there is already an interstellar mission. Other braking concepts might use sails, magnetic interactions, or the target star's radiation and gravity, but each changes the trajectory and mission time. A fast flyby avoids the largest braking requirement, yet sacrifices the ability to remain in the system. The difference between crossing and arriving now becomes an energy distinction. A probe that flashes past the destination keeps almost all its kinetic energy. A rendezvous vehicle must transfer that energy somewhere. It might convert some into radiation, exhaust, stored energy, or momentum carried by another medium, but it cannot simply declare the velocity finished. The propulsion choice also affects acceleration distance. A high-power system might deliver a short, intense push, followed by a long coast. A lower thrust system might accelerate for years. Both could share the same maximum speed, while producing different total travel times. This is why the flight board records the complete velocity profile instead of placing one speed beside one distance. For the ideal one-gravity row, the energy and momentum columns are intentionally blank. Relativity does not prohibit the path. Conservation laws do not provide a single theorem saying no technology could ever follow it. But every known method faces extreme scale, and no demonstrated system can continuously accelerate a useful macroscopic payload to 0.752 c, reverse the momentum exchange, and stop after 1 light-year. This is the central contradiction in its strongest form. The clocks are not the problem. Their behavior is understood and experimentally supported. The distance is not mathematically uncrossable. The obstacle is constructing a complete physical chain, from energy source to thrust, from thrust to protected payload, and from relativistic cruise to controlled arrival. The momentum bill also prevents a common form of technological optimism. Better materials, computers, or manufacturing can improve efficiency and reduce mass. They may enable architectures that are impossible today. Yet efficiency cannot exceed the underlying conservation requirements. A lighter probe needs less energy than a heavier one, but a crewed ship cannot be reduced to a gram without ceasing to be a crewed ship. This is why payload class belongs beside every travel time estimate. 5 years at 0.2 c for a gram-scale sail is not evidence that a human vehicle could make the same crossing with a slightly larger laser. Increasing payload changes the beam, sail, acceleration distance, heat load, structural demands, and braking problem together. The shortest physically allowed time, therefore, arrives with the largest missing machine. To move from an ideal row to a plausible concept, propulsion systems must be compared by where they obtain energy, how they exchange momentum, what payload they move, and how they stop. Every proposed shortcut solves one part of the bill by transferring another part elsewhere. Every propulsion system must answer the same questions. Where does its energy originate? What carries the opposite momentum? How much payload can it move? Over what distance does it accelerate? How does it reject heat? What protects it at speed? And when it reaches the destination, how does it stop? Comparing proposed top speeds without these columns turns engineering studies into slogans. Chemical rockets provide the most mature starting point. Their propellants react, creating hot exhaust that expands through a nozzle. They can produce high thrust and have carried every human beyond Earth's atmosphere. Their limitation for interstellar flight is exhaust velocity. Chemical energy gives each kilogram of exhaust far less speed than a relativistic mission demands, so the rocket equation drives the required propellant ratio to unusable levels long before the spacecraft approaches a meaningful fraction of C. Electric propulsion changes the trade. Ion and related engines use electrical power to accelerate charged particles to much higher exhaust velocities than chemical rockets. They can use propellant efficiently and operate for long periods. But their thrust is usually low and their performance depends on a power source. They are valuable for many missions inside the solar system. Yet efficient propellant use does not automatically create the power needed to accelerate a large interstellar vehicle rapidly. Nuclear pulse propulsion takes a more forceful approach. Historical studies examine spacecraft pushed by repeated nuclear explosions outside a massive shock-absorbing structure. The concept uses known nuclear physics and could offer much greater effective performance than chemical propulsion. However, proposed velocities depend strongly on design, staging, payload, and assumptions. No such interstellar craft has been built. Structural demands, launch safety, treaties, fallout, cost, and the enormous number of pulses prevent a historical study from becoming an available vehicle. Fusion concepts attempt to use the reactions that power stars, directing energetic products as exhaust. Fusion could in principle provide much higher exhaust velocities and energy density than chemical reactions. But controlled fusion for propulsion, fuel handling, ignition, confinement, heat management, and a complete lightweight engine remain unresolved at the required scale. A theoretical fusion exhaust does not establish the mass ratio, thrust, or reliability of a working interstellar craft. Antimatter offers the largest energy release per unit of reacting mass among these commonly discussed concepts. When matter and antimatter meet, their rest energy can be converted into other particles and radiation. That makes antimatter attractive on paper, but an energy source is not yet an engine. Antimatter must be produced, collected, stored without contacting ordinary matter, metered safely, and converted into directed thrust. Present capabilities are nowhere near the quantities or systems implied by a relativistic spacecraft. Each onboard approach fights the same compounding burden. The craft carries the power plant, the engine, the reaction mass, the radiators, and the shielding. Increasing one component increases the mass that every other component must accelerate. More payload requires more energy. More energy conversion creates more heat. More heat demands more cooling mass. Beamed propulsion changes the architecture by moving much of the energy source off the spacecraft. Instead of carrying a reactor and large propellant supply, a lightweight sail receives momentum from an external beam. Photons reflected by the sail change momentum, pushing the craft forward. The departure system remains massive, but the accelerated object can be extremely small. Breakthrough Starshot represents the clearest modern example. Its stated ambition is to demonstrate the foundations for gram-scale nanocraft propelled by an intense light beam to as much as about 0.2 c. At that cruise speed, 1 light-year takes 5 Earth years, and the Alpha Centauri system could be reached in a little over 20 years of flight. This is a proof-of-concept ambition, not an operational mission, and not a plan for passengers. The small payload is the central feature, not a temporary inconvenience. A gram-scale craft requires far less energy than a ton-scale ship. A thin sail can present a large reflective area relative to its mass. Multiple probes could provide redundancy. But shrinking the vehicle also constrains instruments, power, communication, computation, attitude control, and protection. The beam itself becomes a machine of extraordinary scale. It must deliver enormous power, maintain phase control across a large array, focus on a rapidly receding target, and keep the sail stable during acceleration. The sail must reflect almost all incident energy at the chosen wavelength, because even small absorption can produce destructive heating. Atmospheric distortion, weather, pointing, and orbital geometry affect any ground-based system. After acceleration, the probe must survive years of flight without repair. At 0.2 C, the interstellar medium no longer resembles an almost empty background. In the craft's frame, ordinary gas particles arrive as a concentrated stream of high-energy impacts. Published models find that gas can alter materials and produce radiation damage, while dust can melt, crater, or erode the forward surface. This hazard unifies speed, mass, and shielding. A larger shield can improve survival, but it adds mass and therefore demands a more powerful beam. A smaller frontal area reduces impacts, but constrains the vehicle's geometry. Material choice changes penetration, heating, and erosion. The medium does not necessarily make the mission impossible, but it must be part of the design from the beginning. Navigation becomes equally unforgiving. A tiny error in direction grows across light years. The probe cannot receive rapid instructions because commands take years to cross the distance. During a high-speed encounter, the target system passes quickly, giving instruments little time to point, observe, store data, and avoid failure. The vehicle must operate with substantial autonomy. Returning information creates another machine at both ends of the link. A gram-scale transmitter has limited power and aperture. Earth must detect an extremely faint signal across interstellar distance, identify it among noise, and reconstruct the data. Even after the probe completes its flight, the signal requires additional years to return at light speed. Starshot's baseline logic also favors a flyby. The departure beam accelerates the sail away from Earth, but no comparable laser array waits at Alpha Centauri to slow it. Arriving at 0.2 C allows a crossing and brief encounter, not a rendezvous. Proposed braking methods using sails, stellar radiation, magnetic fields, or gravity change vehicle design, and generally extend travel time. None can be added as a footnote to the 5-year per light-year figure. This reveals the pattern shared by every architecture. Chemical rockets carry manageable engines but inadequate exhaust velocity. Electric systems improve exhaust efficiency, but face power and thrust limits. Nuclear and fusion concepts raise performance, while introducing immense unbuilt machinery. Antimatter concentrates energy, but creates production, storage, and conversion barriers. Beamed sails remove much of the onboard power plant, but require enormous external infrastructure and extremely small payloads. Every shortcut creates another machine. If the power source is removed from the craft, a beam array appears at departure. If propellant is reduced, sail precision and pointing become central. If shielding is strengthened, mass rises. If braking is demanded, destination infrastructure or a slower trajectory appears. The constraints move. They do not vanish. This does not make the concepts equivalent or hopeless. Beamed propulsion may offer the most credible path among current ideas toward relativistic gram-scale probes. Nuclear or fusion systems may eventually transform heavier robotic missions. Future discoveries could alter engineering choices. But the evidence does not support moving a concept from the gram-scale column into the crude column simply because both obey the same relativistic equations. A fair comparison cannot rank engines by an advertised velocity. It must ask whether the figure describes exhaust speed, maximum vehicle speed, cruise speed, or mission average speed. It must state the payload and whether acceleration and braking are included. It must separate a physical principle, a design study, a laboratory component, and a flown system. Those categories are evidence levels, not insults. A concept can be scientifically serious while remaining far from construction. Keeping the levels visible prevents an elegant propulsion equation from being mistaken for a launch schedule, and prevents early research from being dismissed because the complete machine does not yet exist. The flight board can now distinguish three levels. Demonstrated systems have moved probes outward at Voyager-like speeds. Active concepts seek to move tiny payloads toward a fraction, such as 0.2 c. Ideal trajectories show what clocks would record if a macroscopic craft sustained one gravity and stopped. These levels answer different questions and carry different confidence. All the pieces are finally present: the measured distance, the tested clocks, the achieved speeds, the ideal acceleration, the energy and momentum requirements, the propulsion trades, the environmental hazards, and the arrival condition. The documentary can now answer the title without choosing one misleading number. The fastest crossing must be labeled not only by time, but by how much of the required machine exists. The 2-clock flight board is finally complete enough to answer the question. It does not contain one row labeled real and several rows labeled false. It contains levels of reality: a speed demonstrated by a departing spacecraft, a record used as a counterfactual cruise, an active concept for a tiny probe, and an ideal relativistic trajectory with no available engine. Each row is scientifically honest only when its conditions remain attached. The first row belongs to Voyager 1. Distance, 1 light-year. Speed, about 17 kilometers per second relative to the Sun. Trajectory, sustained outward coast, used here as a constant speed benchmark. Earth frame time, approximately 17,600 years. Ship time, effectively the same at this precision. Arrival condition, fly past, not stop. This is the strongest row in terms of demonstrated interstellar motion. Voyager is not traveling toward a marker 1 light-year away, but humanity has built, launched, tracked, and communicated with the machine. Its speed is measured. Its outward trajectory is real. The 17,600-year answer is therefore not a prediction of a specific mission. It is a projection based on achieved performance. The second row belongs to Parker Solar Probe's speed record. Distance, 1 light-year. Assumed constant speed, about 192 kilometers per second. Earth frame time, roughly 1,560 years. Relativistic clock difference, still negligible for the rounded comparison. Arrival condition, again a flyby. This row is less operationally real than Voyager's. Parker has reached the speed, but only near the Sun, while following a bound orbit. No existing system has placed it on a straight interstellar escape trajectory while maintaining that velocity. The row answers a counterfactual question. How long would 1 light-year take if humanity's highest measured spacecraft speed could become a sustained cruise? The answer remains roughly 16 centuries. The third row moves from demonstrated spacecraft to an active propulsion ambition. Distance, 1 light-year. Cruise speed, 0.2 c. Earth frame cruise time, 5 years. Onboard proper time, approximately 4.899 years. Payload, gram-scale probe. Propulsion, external light beam and sail. Arrival condition, high-speed flyby, unless an additional braking system is developed. This is not an achieved capability, but it is grounded in a defined physical architecture. The low payload mass is what allows the concept to approach the energy problem differently. The beam infrastructure remains at departure, while photons deliver momentum to the sail. Yet the row does not automatically include launch readiness, sail survival, beam construction, interstellar shielding, navigation, data return, or braking. 5 years per light year is the cruise arithmetic attached to the stated target speed. The fourth row is the fastest complete crossing examined here. The ship begins at rest beside the departure station, accelerates at 1 standard gravity for half a light year, reverses thrust, decelerates for the remaining half, and arrives at rest beside the destination. Its maximum speed is approximately 0.752 c. Earth and the destination record, about 2.208 years. The onboard clock records about 1.892 years. Every kinematic field in this row is defined. It includes acceleration and braking, rather than hiding them outside the measured course. It produces a rendezvous rather than a flyby. It respects the speed of light and follows established special relativity. In that limited but important sense, it is physically honest. It is not technologically honest if presented as something humanity knows how to build. The row assumes a propulsion system capable of accelerating a macroscopic protected vehicle almost continuously, supplying the required energy and opposite momentum, managing waste heat, surviving relativistic gas and dust, operating without repair, reversing thrust, and stopping. No demonstrated or designed system closes all of those requirements. The hierarchy resolves the apparent disagreement between thousands of years and less than 2. 17,600 years is the achieved speed benchmark. 5 years is a conceptual relativistic cruise time for an extremely small probe. A little under 2 traveler years is the proper time along an ideal 1 gravity world line with a stopped arrival. The numbers do not compete because they describe different vehicles, paths, clocks, and evidence levels. The arrival condition reveals another difference among the rows. The Starshot-style probe is primarily a flyby concept. Only the 1 gravity row explicitly ends beside the destination at rest. If all rows were forced to include braking, their durations and engineering requirements would change. The apparent ranking is therefore not a race among equivalent missions. Payload changes the comparison just as strongly. A gram-scale probe may carry sensors and communication hardware, but it does not carry people, habitat, redundant life support, or heavy shielding. The 1 gravity calculation leaves payload unspecified, while its acceleration can tempt viewers to imagine passengers. That image must remain conditional. A comfortable acceleration profile says nothing about whether a crewed vehicle can supply or survive it. Now consider the one-year answer. The departure and destination are stationary relative to each other and separated by 1 light-year. In that frame, light crosses the interval in 1 Julian year. A massive spacecraft must move below light speed, so its endpoint frame crossing time must be greater than 1 year. It can approach that limit as its velocity approaches c, but it cannot equal the light signal. The traveler's clock is different. As speed rises, the proper time accumulated along the ship's path can become much shorter than the endpoint frame duration. This does not allow the craft to reach the destination before light in the endpoint frame. It means the ship follows a world line that contains less proper time between the same departure and arrival events. At the boundary lies the major exception: light itself. A light ray follows a null path through space-time, and the proper time along that path is 0. This is often translated into the statement that a photon experiences no time. That phrase is memorable but imprecise. There is no valid inertial rest frame for a photon, so physics does not define a photon's viewpoint with an onboard clock. The 0 proper time of the light path does not offer a state that a massive traveler can gradually enter. As the ship approaches c, gamma, energy and momentum grow without bound. The craft can make its own elapsed time arbitrarily small in an ideal sequence of ever faster trajectories. But every step demands more energy, and no finite step reaches the null path. This exception sharpens the answer instead of erasing it. Light sets the endpoint frame boundary. Massive travelers occupy time-like paths below that boundary. Their proper time depends on the path, but their motion never becomes light-like. The 1 light-year ruler and the 2 clocks remain fully consistent. The intellectual achievement is not a futuristic engine. It is the ability to distinguish what is measured, what is established, what is proposed, and what is ideal. Bessel's parallax gave the stellar ruler. Einstein's relativity gave the relationship between the clocks. Particle experiments showed that the relationship belongs to nature. Rocket physics supplied the momentum cost. Voyager and Parker established the scale of demonstrated motion. Starshot exposed how radically payload must shrink before relativistic speed becomes a serious engineering target. These threads converge on a result that is both more hopeful and more restrictive than the simple answer. The universe does not require every traveler to personally endure thousands of years for each light year. Relativity permits a human-scale proper time. But the universe does require a physical mechanism to create the necessary world line, and every kilogram, joule, momentum exchange, impact, and braking maneuver remains part of that mechanism. The fastest mathematically specified crossing is therefore not the most credible near-term mission. The most credible existing spacecraft produces the slowest row. Between them lies a ladder of concepts, whose times shorten as their unbuilt infrastructure grows. This inverse relationship is the climax's complication. The better the stopwatch result becomes, the less complete the machine behind it is. The flight board should now be read from both directions. Read downward by time, and the journey shrinks from millennia to years. Read across by evidence, and certainty changes from measured hardware to engineering ambition to idealized motion. No single row is allowed to borrow confidence from another. Voyager's existence cannot prove Starshot's readiness. Starshot's known physics cannot prove a crude one-gravity ship. The validity of the one-gravity equations cannot supply their missing engine. Yet the ideal rho remains valuable. It identifies the target a propulsion system would have to meet. It tells designers the maximum speed, the acceleration history, the two elapsed times, and the arrival condition. It transforms a vague dream of near light speed into a defined physical challenge. Failure to build it today does not make the calculation fiction. Presenting the calculation as available technology would. The central question can now receive its strongest answer. How long would it really take to travel 1 light-year, with demonstrated outward spacecraft speed, many thousands of years? With a serious gram-scale relativistic ambition, about 5 Earth years of cruise, at 0.2 c. With an ideal continuously accelerated ship that stops, about 2.208 Earth years, and 1.892 years aboard. The remaining uncertainty is no longer hidden inside the word really. It has a name: propulsion architecture. It includes the energy source, momentum exchange, payload mass, heat rejection, shielding, autonomy, communication, and braking system. Relativity tells us how the clocks will respond if that architecture succeeds. It does not tell us which civilization, technology, or century will succeed. The final answer must therefore preserve two truths at once. 1 light-year is not inherently a 17,000-year experience for every possible traveler. It is also not a 2-year trip humanity presently knows how to make. The distance is fixed. The clocks are understood. The machine remains the open frontier today. So how long would it really take to travel 1 light-year? With a spacecraft moving outward at about Voyager 1 speed, approximately 17,600 years. That is the answer anchored most directly to demonstrated interstellar motion. Voyager was never designed to cross a measured light-year or rendezvous with another star, but its sustained heliocentric escape speed gives us a real baseline. At that velocity, the ship and Earth clocks remain effectively aligned for this estimate. If humanity's highest measured spacecraft speed could somehow become a permanent straight-line cruise, the answer would fall to roughly 1,560 years. Parker's solar probe reaches about 192 kilometers per second near the Sun, but only during passages through a powerful gravitational field on a bound orbit. The 16th century result is therefore a counterfactual comparison, not Parker's destination or an existing mission capability. At 0.2 c, 1 light-year requires 5 years, according to the endpoint frame. A clock coasting with the probe would record approximately 4.899 years. This speed belongs to ambitions for gram-scale light-driven probes, not to demonstrated spacecraft or passenger vehicles. It also describes cruise after acceleration and before any braking. A fast flyby is not the same achievement as arriving at rest. Under the most ambitious ideal trajectory examined here, the craft starts at rest, accelerates at 1 standard gravity for half a light-year, reverses thrust, and decelerates for the second half. It arrives at rest after approximately 2.208 years on the endpoint clocks. Travelers aboard record about 1.892 years, and the ship reaches roughly 0.752 c near the midpoint. Those numbers are allowed by tested relativistic kinematics. They are not supported by an available propulsion system. No known machine can maintain that acceleration for a macroscopic protected payload, supply and redirect the required momentum, manage the energy and heat, survive the interstellar medium, and stop after 1 light-year. The trajectory is physically defined but technologically unfulfilled. Light itself crosses the distance in 1 Julian year, in the frame where the endpoints are 1 light-year apart. A massive spacecraft must take longer than 1 year in that frame, because it cannot reach C. Its onboard proper time can be shorter than 1 year, on sufficiently fast trajectories. But that does not let it arrive before light. The endpoint and traveler clocks measure different intervals along different paths through spacetime. There is therefore no single honest number without conditions. The duration belongs to a complete statement. This payload, following this acceleration profile, read by this clock, with this arrival condition. Remove those labels, and a correct calculation can become a misleading promise. Return to Voyager's stopwatch. The probe continues outward, while its signals weaken, and the distance from the Sun grows. Against the 1 light-year course, its progress seems almost frozen. Yet Voyager should not be remembered here as evidence of failure. It reveals what humanity has actually achieved, and gives every future proposal a measured starting point. The next major change is likely to appear first, in tiny uncrewed probes. Reducing payload reduces the energy and momentum that must be supplied. External beams may avoid carrying an entire power plant and propellant system aboard the craft. Even then, sails, beam arrays, navigation, shielding, communication, and target encounters remain unresolved engineering challenges. Moving from Voyager's row toward the 5-year row requires not one invention, but a connected system. Moving from a gram-scale flyby toward a stopped, crewed journey is a far larger transformation. Passengers require habitat, life support, reliability, and protection. Every added kilogram must be accelerated and later decelerated. A comfortable 1 gravity profile describes how the passengers would feel if the thrust existed. It does not make the engine, shield, or braking system easier to construct. The frontier is therefore not whether special relativity works. Moving clocks, particle lifetimes, and relativistic energy have been tested repeatedly. The uncertainty lies in whether engineering can create a spacecraft that uses those laws at a useful scale. Future systems may improve exhaust velocity, relocate energy into beams, reduce payload, or discover better ways to brake. None can remove conservation of energy and momentum. The title's answer can now be stated without contradiction. 1 light-year takes about 17,600 years at Voyager speed, roughly 16 centuries at a hypothetically sustained Parker record, 5 Earth years at 0.2 C, or about 2.208 Earth years and 1.892 traveler years on an ideal continuous 1 gravity journey that ends at rest. The fastest number is not the most available, and the slowest is not the most fundamental. They occupy different rows on the same board. One measures current hardware. One extends a record beyond its actual trajectory. One describes a serious but unproven tiny probe ambition. One defines what relativity permits before engineering supplies the machine. That machine may begin as a tiny probe, carrying no passengers and returning data. Its importance would not come from matching science fiction. It would come from changing the measured row on the board. For the first time, an object built on Earth would cross interstellar distance on a timescale connected to a human life. A light year remains a fixed distance. The time it demands is a record of the path, the clock, and the physical system carrying that clock through space. We already understand the ruler. We understand why the clocks disagree. What we do not yet possess is the machine that can turn the shortest honest calculation into a journey.